Welcome to this little tutorial on momentum calculations. This is 2024. Here we have Jono. He releases his 10 kg dog and it runs directly towards the neighbour's dog at 1.1 meters per second. The neighbour's dog has a mass of 12 kgs and runs directly towards Jono's dog. They collide, stick together and slide across the floor at 0.30 meters per second. We need to calculate the speed that the neighbour's dog was moving at before the collision. It's important to realise for such a question, you need to understand that momentum is conserved. And so the momentum initially is going to be equal to the momentum after the collision over here. So the equation that you need to use will look something like this. And I always like to create a table to be able to treat these two components separately. And so the initial momentum is going to involve the initial momentum of the neighbour's dog. I've titled him N. And the initial momentum of Jono's dog. And I've titled this dog J. And so here we have it. We need to calculate the initial momentum, the total initial momentum before the collision. The way we're going to do that is using this equation here. Momentum is calculated by an object's mass times its velocity. And so let's start off by calculating the initial momentums of both the dogs. And so I've just coded N for the neighbour's dog, and here we have its mass times its initial velocity, and then Jono's dog's momentum, which is its mass times its initial velocity. Notice that I have these arrows up here, and because momentum is a vector value, this means that it not only has a size, but it also has a direction. So I, for the sake of this example, am creating the neighbour's dog to have a positive velocity in this direction, which is signified by the diagram, and Jono's dog, its velocity is going in the opposite direction, so it is going to be a negative value. And so these velocities, since they're going in opposite directions, they should be oppositely assigned in terms of positive and negative. Final momentum can be calculated by the neighbour's dog's mass times its final velocity, and Jono's dog's mass times its final velocity. They're both going in the same direction, so they're both positive vectors. Now we can start to substitute the numbers in. So for the neighbour's dog, it has a mass of 12 kgs. We don't know its initial velocity. That's what we're trying to find, and we're going to have to rearrange this whole thing in the end to find this. Jono's dog has a mass of 10 kgs, and its velocity is 1.1 meters per second, but because it's going in the opposite direction, to the neighbour's dog, this velocity vector is going to be a negative value like this arrow here. So this is why I've written negative 1.1. Let's move on to the side of final momentum. So we have the neighbour's dog, still 12 kgs, nothing has changed in mass, times the velocity of 0.30 meters per second, and the same for Jono's dog, except obviously the mass of Jono's dog is 10 kgs. Next up, let's go back to the momentum initial column. Let's simplify this a little bit more. So I've just simplified, I can't simplify this anymore, so I've just left it, but I can simplify this bracket here. 10 times negative 1.1 is negative 11. Let's see if I can simplify the other side. Of course I can. 12 times 0.30 is 3.6. And then we've got 10 times 0.30 is 3. Let's see if I can simplify this even more. Here's what I want you to know. Whenever we have a positive outside of something that is negative within a bracket, I need you to understand that the negative is what kind of trumps over this positive. And I want you to understand in another way that this positive value, this plus sign, is attached to an imaginary 1, okay? So it's an imaginary 1, positive 1. And I also want you to know that whenever you have brackets is another way of multiplying, okay? So whatever's in the brackets is always multiplied directly by what's outside of it. In this case, it's a positive 1 times a negative 11. That gives me negative 11. So that's how I've simplified this, okay? So this is why we've got a negative 11 here as a simplification of this over here. Can we simplify this side? Yes, we can. So I've merged these two things together. 3.6 plus 3 is 6.6. We don't have to worry about the letters. They're just my code to make this clearer for you. Focus on the numbers only. Okay, now we can use a little bit of algebra to finally simplify, rearrange to find out what the initial velocity was for the neighbor's dog. So here we have it. This is the first line of working. We've got the neighbor's dog's momentum value, which I cannot simplify further, attached to a minus 11. The way I get rid of minus 11 is to do the opposite. So I plus it by itself and that gets rid of it. And so if I do that on one side, I have to do it to the other side. Now what I can do is I can simplify and solve on this side of the equation. So that's the next step. So as you can see, there's no more 11 because I've cancelled it out like this by plussing it by itself, because the opposite of negative 11 is plus 11. So I've undone it. And now 6.6 plus 11 is 17.6. So I've simplified that. The next step would be to get rid of this 12 times VI. Okay, so the way I can get rid of 12 times VI would be to do the opposite of times 12, which is divide by 12. And so if I divide by 12 on one side, that cancels it out here. That means I have to divide by 12 on this side. So finally, now that I've got rid of times 12 on this side, I'm left with VI equals 17.6 divided by 12, which is 1.47 meters per second, to 3 significant figures. And that is how we solve and calculate the speed of the neighbor's dog before the collision.